Welcome to Study Loop.
This is chapter 27, problem number 18. We have a helium particle that is going horizontally with the initial speed v0, and it's entering a region where there's a magnetic field perpendicular with respect to it. We are first asked to calculate the diameter of the circular trajectory that the particle is forced to go through. So as we know, QVB sine theta, which is the magnitude of the magnetic force, equals to the centripetal force mv squared over r. In this case, sine theta being the angle between V and B. In this case, it's 90 degrees. Sine 90 is 1, so this entire term equals to 1. From here, we can say QVB is going to be equal to mv squared over r. Now we are trying to determine not the radius, but the diameter. So we're looking for the diameter, which is 2 times r. Let's isolate r out of this equation. It's going to be equal to mv squared over qvb. We have b's that are going to cancel out, so mv over qb is going to be equal to the radius. If you multiply both sides by 2, then we're getting the diameter. So now let's plug in the numbers. 2 times the mass is given to us as 6.64 times 10 to the power of negative 27 times 35.6, the initial velocity in kilometers. So I'm going to convert that to meters by adding times 10 to the power of 3 meters per second over, we have Q. Well, a helium particle, it has 2 protons and 2 neutrons. So neutrons don't have any electric charge. The proton of a single, this charge of a single proton is 1.6 times 10 to the power of negative 19 coulombs, but we have 2 of them. So I'm going to add that here, 2 times 1.6 times 10 to the power of negative 19, and times the magnitude of the magnetic field that is given to us as 1.8 Teslas. So if we do this calculation, we get to 8.3 times 10 to the power of negative 5 meters for the diameter of the trajectory. So in part B, we are asked to calculate whether or not this magnetic force has any effect on the speed of the particle. No, it does not, because the magnetic force is always perpendicular to the speed, the velocity vector, and therefore FB does not do work. Right, and if that's the case, then the FB has no effect on the speed, which is basically the magnitude of velocity, right? It has no effect on the speed. However, as we're going to see, it actually changes the direction. So we have to think in terms of separately in terms of magnitude and the direction. So yeah, FB has no effect on the speed. Now, in part C, we are asked to calculate the acceleration on the charge. So again, from Newton's second law, m times A equals QVB in this case. And if we were to calculate the acceleration, we would divide both sides by the mass, right? To isolate A here, it will be QVB over M. Now, when we plug in the numbers, remember Q was 2 times 1.6 times 10 to the power of negative 19 coulombs. V is given to us as 35.6 times 10 to the power of 3 meters per second. And the magnitude of B, it was 1.8. We're going to divide this by 6.64 times 10 to the power of negative 27 kilograms. So what we get for acceleration is 3.088 times 10 to the power of 12 meters per second squared. This is the answer to part C, to be specific. And this is the magnitude of the acceleration, but how about the direction? Direction of acceleration, it's always going to be towards the center of the circular trajectory that we're talking about. Always towards center of the circular trajectory. So in part D, we are asked, whether or not the force being perpendicular to the velocity vector, whether or not the magnetic force would change the direction or the magnitude of it. As we all know by now, combined with the answer to part B, it only changes the direction of the velocity vector, but not the magnitude. Again, the speed is constant throughout this motion.